My name is Amin Kinaben. I am the tech lead for the Tanzu Kubernetes Grid multi-cloud Windows offering here at VMware. I am a contributor and collaborator for Sig Windows and Sig Network upstream. This talk will be about running your own workloads on hybrid OS clusters inside Kubernetes. The first idea is to give an introduction and the motivation behind running hybrid OS clusters in a production cluster. We're going to see the available capabilities that Calico can offer in a Windows cluster and a few examples of possible environments created with the development and production modes. To wrap up, we are going to see the advances in the Sig Windows host process container research upstream. Windows clusters constitute a large portion of the services and applications running in many organizations today. Hybrid node clusters are a requirement for the modern enterprise. Platform engineers and SRE need a concise way to orchestrate heterogeneous workloads on Kubernetes. So it's important to have this kind of environments in the modern enterprise because legacy workloads still need to run in a modern environment with Kubernetes in place. Kubernetes support Windows nodes with process isolation only. Hyper-V is still not supported upstream. Network on Windows works the same way as the CNI plugins runs on the Linux box. The Calico CNI has Windows support in multiple providers, AKS and AKS for example. This table shows the comparison across the Windows components and the Linux components in terms of networking. So in the Windows side, we can call a network compartment. In the Linux component, we have the network namespace. The next layer, you have the vSwitch or the HNS network as a layer 2 and layer 3. For the Linux side, you have the bridge and the IP route. Going on, you have the HNS endpoints. That's where you can bound your vSwitch port, and the Linux component, you have the IP links. The last layer is the HNS policies or the filtering engine. And one example in the Linux is the IP tables. The available capabilities in the Calico CNI for Windows. For the networking side, it includes IPv4 only, Calico running with the BGP mode without overlays, and Calico supports VXLAN as an overlay. For the network policies, it works as well. The blog post below shows one network policy conformance that we wrote 1 year ago. You can use this to test your cluster and validate the network policies or conformance with the specification defined here in this blog post. To finish up, we have the manifests installation. You can install Calico on Windows in two ways. First one is the PowerShell script. So you can run a PowerShell script to install Calico. And the next one is a host process container installation. That's more easy to install and straightforward. One way to use the Calico CNI is testing with the Sig Windows development environment. This is the official Sig Windows fully batteries included development environment for Windows. You can run a Windows cluster locally with the latest Kubernetes and Calico CNI. Currently, we only support Windows 2019. We use Vagrant and VirtualBox on your own machine to bring a Linux and a Windows node and a complete Calico running environment for tests. We use the image builder project to build the Windows VirtualBox image inside the project. The image builder project uses Packer and Ansible in a series of steps and tasks that installs everything that's required on top of the ISO installation image of Windows. As you can see in the diagram, you run a make target with some modifications from the Sig dev tools. The make target starts Packer from HashiCorp with the VirtualBox hypervisor. In the sequence Packer provisioning, all the steps required via Ansible. So installs the Kubernetes, prepares the system, installs the Windows updates, cloud-based init, and the runtime. In sequence GAUS is used to verify the services installed correctly. In the end, Packer post-process the image and return this VirtualBox package that can be used and imported inside the VirtualBox project. The installation is pretty straightforward. The provisioning part runs a PowerShell script in the end of the box setup. It copies the config ps1 file from the host. You can change the config ps1 from the forked directory to adapt for your own configurations. The next step is install Calico PowerShell, and this will bring all the requirements and components of Calico in your Windows node. We start the service Calico Felix and Calico node as a Windows service. We check if they are running. In the end, we install Kube proxy as a service as well with the install Kube services script. The automation here is made by this PowerShell script that goes through all these steps to install the Calico as a service on your Windows. Having an overview of this diagram, we have the user running Vagrant to start a new cluster. Vagrant provides all the required machines on VirtualBox. So the first one is a 10, 20, 30, 10, and this is the Linux control plane. This installs all the control plane components like API server, scheduler, and controllers managers. The second node is the Windows workload. The Windows workload runs on 10, 20, 30, 11, and this IP exists on an internal private network between the nodes. Now we are gonna see a demo of the Sig Windows dev tools. So the first step is to start the control plane. Control plane startup depends of downloading all the Kubernetes binaries from the internet. Next, the control plane virtual machine is started on the VirtualBox. The script installs all the dependencies. Now the control plane starts itself with kubeadm init. Next steps, Calico installation. So the Calico installation is automatically made in the system. So starting the Windows node. The second step is starting the second node in the system. The VirtualBox exists on Sig Windows Dev Tools, Vagrant Hub. And the first step is the installation of the VirtualBox guest editions. The ISO is automatically mounted and is installed in the Windows machine. kubeadm join steps comes next. And as soon as the kubelet starts and joins the node, it installs Calico CNI in the sequence through a PowerShell script. Smoke tests. To guarantee the node and the cluster are working, we basically run a few smoke tests that starts a deployment in the Windows node and another deployment in the on the Linux control plane, and make them curl each other, the web services on each node, to ensure the communication is working and Calico is working properly. Another feature that exists in the Windows machine is the capability of SSH into the machine and run Vim to configure your code automatically. For the production environment, we use Cluster API. This is a more complete solution to run production-ready entire clusters. So Cluster API is a Kubernetes sub-project focused on providing declarative APIs and toolings to simplify provisioning, upgrading, and operating multiple Kubernetes clusters. It supports multiple cloud providers, CapZ, Kappa, or CapV. The installation is kind of straightforward. So the user uses a Kubernetes cluster to create objects, and the controllers inside this Kubernetes cluster will spin up and manage the life cycle of the other clusters. In the example here, you can have a management cluster, that's the base cluster, that you install your objects to start new clusters. The workload clusters that are spinned up in the right side can be hybrid OS clusters, can be Windows only clusters, or Linux only clusters. Going further, the Cluster API can provide a cluster class definition. What is the evolution of a cluster definition? So the advantage that you can have on cluster class is to have multiple machine deployment classes. So it allows you to reuse the MD machine deployment objects across different clusters, as well as the kubeadm templates. It's easy to adapt via variables, and it's easy to extend via runtime extensions and patching lines. The main goal is to have a hybrid cluster with machine deployment classes and this via cluster class that can be defined and reused in different places. This blog post explains better how the migration for cluster class and this new object specification works. In this example, we have a diagram of a cluster that points to the cluster class called hybrid. The object is of the kind cluster. You can define in the field workers a few machine deployments. It can be like a machine deployment class of Linux worker or a machine deployment class of Windows workers. You can call this a node pool. This node pool can have different nodes number in the replicas field. So machine templates reused with a predefined Calico installation. This new object cluster in the management cluster, a new cluster will start and be created by your infrastructure provider. One way to change these specifications in your cluster is through patches and variables. So your cluster class can have some logic inside of that to evaluate if the JSON patch can be applied or not, for example. Here we can see that a few modifications in the entire template exist with a JSON path of type operation add for the node registration CRI socket, for example. This way we override pipe used by containerd for the Windows. So we can reuse the same kubeadm config templates for different places and at runtime patch them and modify its content. Another way and better alternative to modify these patches is the runtime extensions. So you can, through imperative and Golang, write a webhook that modify this in flight. So you can have tests and you can have a better coverage and reliability of your changes. Installing the CNI on Cluster API is made by changing objects and installing new objects inside the new cluster. So the cluster resource set object can be used to start the CNI after the cluster is created. This is true for Linux, where you can install host process containers, CNIs, and kube proxy. This will automatically bootstrap the CNI for you. On Windows, if you're using PowerShell, we need another mechanisms to do this installation. The first step is to use the object kubeadm config template for a cluster and change the post kubeadm commands to point to your own CNI installation scripts. What this command does is to run the CNI installation after your node joins the cluster. So as soon as it joins, you can install the CNI automatically on each new node that's created that is using this config template set here in the object. The other way to run Calico inside a cluster, and this is the modern way to do that, and the most Linux parity way to do that. So you run Calico as a privileged container, as a host process container inside the Windows. It's required to add the security context host process in the daemon set. Security context will have host process equal to in the Windows options. This will enable the Calico to run as a process inside the Windows, but the lifecycle is still managed by Kubernetes. You need to set host network equals true as well. So the IP of the Calico will be the same IP of the node that it's running. In the spec, we have the init container. This is required to install and copy all the CNI binaries and configurations inside the hood of your Windows node. Next, the host process container have the containers spec with the Calico node startup and Felix. Both will have and will start the services as a host process container. Kubeproxy runs as another daemon set, and this is an example of the specification of Kubeproxy as well. It means no more Windows services, and this is a good thing for the parity of functionalities across nodes inside Kubernetes. Before jumping in the demo, I want to highlight what we saw so far. So the first thing the user can do is create a cluster class. The cluster class defines the machine deployments that has all the configurations required for a cluster to run. Second, the user can create a cluster object, and on your workers field, it defines the machine deployments and calls the machine deployments set in the cluster class. The infrastructure provider will bring a new Azure VM and will create and install the Kubernetes node for you based on your workers definition and the replicas you set in your workers specification. The third step is to install a cluster resource set in your cluster. And this cluster resource set is responsible to install the Calico and Kubeproxy as host process containers. This way you can have a working Windows cluster running on Azure. Now we are going to see a demo of the host process container on an Azure cluster. Now we run kubeget pods to list all the pods in the system and get the Calico node that's running inside the Windows machine. So describing this pod, we can see exists that there is the install CNI as the bootstrap, Calico pod, Calico container, and Calico node startup and Calico Felix are running as well as host process containers inside the Windows node. The same happens for the Kubeproxy Windows. Kubeproxy is now running as a host process container. We are going to do another smoke test running a web server on the Windows and curling it from the Linux pod to another Linux pod. Let's apply both specs. The Windows has a service on it as well. So at this point, we can see both pods are running on different nodes as a host process container running in the Calico running as a host process container. The IP are distributed here for each pod. We enter in the Linux machine, in the Linux container, curl directly the Windows IP on the service 9376. The container is listening on this port as a web server. So we get a host name as the return. And now we are going to access the service directly. That should have the same result. To wrap up, we have some resources listed on this presentation. Calico installation on Windows. This is the main documentation and official documentation that provide you all the resources required to bootstrap your own version of Calico. The Sig Windows Development Tools is a Kubernetes Sig tool that's available for download and testing. This article, Debugging Windows Cluster, is a very good article to understand the inners of Windows networking and Windows systems inside Kubernetes. The last resource here that we have is the Windows Tools repository. We have a few examples of Flannel CNI, Calico CNI in the upstream repository. Shoutouts to a few Sig Windows members: Jay Vias for starting the Dev Environments project and adding Calico CNI as an option, Mark Rossetti and James Sturtevant to bring Calico as the host process container upstream. Thanks.